This is my recording on Lab 2, projectile motion. The purpose of this lab is to compare the real projectile motion of an object to the predicted projectile motion of an object affected by gravity and drag. Another purpose of this lab is to understand the principles of Newton's second law and the effects of drag force. Here are some important equations to understand for this lab. Newton's second law, which states that force is equal to mass times acceleration. Velocity update formula, which states that the final velocity is equal to initial velocity plus the net force divided by mass times time. The position update formula, which states that final position is equal to initial position plus average velocity times time. Drag force, which is a fluid resistance force that opposes an object's motion through a fluid like air or water, with the equation being negative b times velocity squared times the normal velocity, b being a constant of proportionality, meaning it is dependent on the object's shape and size. Gravitational force, which is mass times gravity, and the net force in this case, in my lab, is negative mass times gravity, being the gravitational force, minus b times v squared times the normal v, which is the drag force. To begin my lab, I first had to choose a system, which was a ball of paper, and the surrounding, which was everything else. First, a video was taken of the ball of paper being thrown across the air. And that video was imported into Tracker, which allowed me to observe the trajectory of the ball of paper. Using data from Tracker, I was able to create a glow script code that generated a computational model of the trajectory of the ball of paper. I predict that in my lab, the computational model that only includes gravity as the force will have a trajectory that goes farther than the real-life model, as there is not an opposing drag force. The computational model that does include drag force will have a similar graph to the real-life model. However, it will not be completely accurate due to some other unknown factors. And these are the initial conditions for my lab. The initial position and the final position were taken from the tracker video, and the mass of the ball of paper was 0.005 kilograms. The initial velocity in the y direction was 2.94 meters per second, and this was calculated using the velocity update formula. The final velocity in the y direction at the tip of its trajectory is 0. Thus, by using this fact, I was able to find the initial velocity in the y direction using the equation gravity times the time it would take to get to the top. The initial velocity in the x direction was calculated using the change in the position in the x direction divided by the change in time. Thus, I was able to get negative 0.8633 meters per second. The time interval of my experiment was 0.6 seconds. And here's my tracker data. On the left is a table of the ball's trajectory in the y and x direction versus time, and the right is a graph of the paper ball's trajectory in the y versus time, along with the original tracker video. And here's my code. The lines of code that are highlighted are what I changed to help best match the computational model to the in real life model. The computational model that did not include drag force had the b set to 0. Thus, the net force only included force of gravity and not force of drag. However, in the computational model that did include drag, I tested multiple b's, and the b that I found that best helped match the computational model to the in real life model was 0.0094. And here are the results. The green line is the computational model that did not include drag, the purple line is the computational model that did include drag, and the blue line is the observed trajectory of the ball of paper. And as you can see, my hypothesis was correct, as the green line that did not include drag went farther than the observed trajectory of the ball of paper. However, the computational model that did include drag, although similar to the observed trajectory of the ball of paper, was not completely the same. This is most likely due to the irregular shape of the ball of paper, as well as the ball of paper's rotation through the air. There could have also been some discrepancies in the tracker data. And here are my questions. The top graph is the velocity versus time graph of the computational model that did not include drag, while the bottom one did include drag. Both models do not predict terminal velocity, as the experiment was over a short course of time. In order for my model to predict the terminal velocity of my object, the object would need to stay in the air for a longer period of time. In this scenario, the time it would take for the object to reach the ground would stay the same as it did in my original experiment. And this can be proven using the velocity update formula to find the time it will take for the object to reach the top of its trajectory. The equation being t is equal to the initial velocity in the y direction divided by g. As the initial speed and no forces would change in both scenarios, nothing in this equation would change. Thus, the time it would take for both objects to reach the top of their trajectory would be the same. And as the time it would take to get to the top is the same as the time it would take to reach the bottom, the total time in both scenarios would be the same.